Okay, so welcome back to another video. So here we have a nice little calculus exercise we'd like to do, and that is to sketch the following function. So we have that f of x is equal to the absolute value of x raised to the absolute value of x for x does not equal 0, and we have another output that is 1 such that x equals 0. So we have something, of course, with piecewise function yet again, but we have an absolute value of raised to an absolute value, so that's something to consider more of a case-by-case situation. And a little bit of a point to make is that when we create this, we have when x is equal to 0, mainly because in the world of calculus, aka the baby of math analysis, that 0 to the 0 power, if you were to plug this back in, is actually considered an undefined expression. Meanwhile, if you're in the world of algebra, then 0 to the 0 power is equal to 1, so you might not see that as a big deal. But here, this is calculus, so I want to make this a little more, clear in case people get into a little bit of controversy, which it's already controversial enough to begin with. So how curve sketching works is, for anybody that's new to calculus especially, is that we are given some function, and of course, we're going to do this without putting this in the calculator, so that's the whole point of why this video was created. Curve sketching is the way that you want to do this is you want to take the first derivative and the second derivative of your function. First derivative actually determines how, depending on where after you find your critical points, meaning you set your derivative equal to 0, that determines on which side is increasing on the side of the function from the left or right hand side, or decreasing, vice versa. For the second derivative, that determines the concavity. So concave up is like this slope, and then concave down is this way. So that's also to determine how concavity works. But if you set the second derivative equal to 0, that determines the point of inflection where indeed it changes that concavity where it's at. It's just something to keep in mind, but for anybody that knows how to do curve sketching, well, big up to you. So that's how we're going to do this. Just curve sketching is, again, a nice little calculus exercise. I didn't find this in the textbook, actually. I just looked this up and thinking this actually works perfectly. So with all this and everything in mind, so now let's actually just jump right in. Okay, so I'm going to actually give you something of a bit of a heads up. Well, rather, I'll write this down. So f of x, we have two outputs, absolute value of x to the absolute value of x, okay? So this is something nice that if you pay attention closely, that if I were to plug an input negative x, for example, so I have the absolute value of negative x to the power negative, or to the power the absolute value of negative x. So in other words, that's the same thing as x to the power x, which is indeed the same thing as f of x if we're dealing this with x strictly greater than 0. What does this imply? This is actually an even function. So what's great is that this actually saves a lot of work because, again, with absolute value, you do with case by case. It's an even function, so yet again, dealing with symmetry about the y-axis. So basically, we only just want to look at one side and rather having to look at both sides because, again, this is based on symmetry. So it's reflecting over the y-axis is going to match the same, especially how the curve is sketched. So that's great. So without that loss of generality, we're just going to focus things on the positive side. So x strictly greater than 0. So with this, symmetric over the y-axis, and then now we're just looking at strictly all the positive numbers, so positive real numbers. So now let's actually determine which side's increasing, which side's increasing. So now let's take our derivatives, so f prime of x. So if we're looking at positives, that means we're just looking at x to the x. We can actually disregard the absolute signs. So if you solve all this out and then you actually apply some logarithmic differentiation of this, so I'll save the work, that's a common exercise when you're in an introductory calculus class. So we'll get that this is x to the power x, and then multiply with ln of x, add this with 1. But to make things a little bit easier and another way to look at things in the retrospect of how we graph things, let's actually write this as e to the power x times ln of x. And then now keep that at ln of x plus 1. So now we must find our critical points. So set this equal to 0. So what we have to do, so f prime of x is equal to 0, which I'll put this as the same thing, e to the power x times ln of x, and then ln of x plus 1. We have to look at things, we have to show that e to the x to the ln of x is equal to 0 and ln of x plus 1. Although that saves the trouble because no solution exists for e to the power x times ln of x because it's a strictly increasing function, so nothing approaches 0. So that means so in other words, no real solution exists for here. So now what's left is just find what ln of x plus 1 is equal to 0 for x. No harm done that this is very simple algebra here, so subtract the 1, then I have ln of x is equal to -1. Just take the exponential to both sides, so the e base, and so therefore we have that x is equal to e to the -1, or in other words, 1 divided by e, approximately 0.367. Just a little, I find this a little bit ironic that we're not actually using a calculator, but I know, and a lot of you will say the same thing, that we actually plug in the value 1 over e just to get an approximate numerical result, because we can't, at least for me, I can't actually get that at the top of my head exactly. But as long as you're showing the work instead of just sketching the graph without no work supported by it, then your teacher's gonna be okay with it in the end. Okay, so x is equal to 1 over e, that's our critical point. So if I plug this back in for back to our regular function, so f of x, so f of 1 divided by e, so in other words, that's the absolute value of 1 divided by e, raised to the power 1 divided by e, and approximately that actually leads to about 0.6922. So that's something to keep in mind whenever we sketch our graphs. So another step you can do, anybody new to curve sketching when you're in the world and dealing with calculus for the first time, a good way to do this is you can actually try a bunch of points, but stick with something easier, for example. So we don't have to do anything decimal. Stick with maybe something with integers and plot those points, but don't sketch anything, just so we can get an idea on like the shape and to some extent. So 0.6922, so at f of 1 over e, that's where our critical point is. In other words, that's where the slope approaches, that's where the slope is 0. So now next thing we have to do is we need to figure out where is it increasing, where is it decreasing between the left and the right of our critical point. So of course we're dealing this with positives, so, and this is our only critical point, just to put that out there. So I have now, we're dealing with positives, so 0, strictly less than x, strictly less than 1 over e. And a good rule of thumb is whenever you're dealing this in this terms of exercise, what you like to do is you want to like graph this out like a numbered line. So actually, let me actually switch to a different marker for this. So I'll make an open dot, and then the critical point over here is 1 over e. Okay, so again, I find it ironic that we have to plug in values into calculator because we can't get the exact number on the top of our head, which is okay. Justify saying that you showed the work before you do, after sketching out your graph. So if you plug things in, so 1 over e, in other words, that's the same thing as approximately 0.367. So plug maybe 0.3 into here. So what you'll yield out back to your f prime of x function, that's where you want to plug, and that determines whether it's increasing or decreasing. What this leads is that any number in between 0 and 1 over e, so I should make an open dot over here, not a closed dot, because closed means that's inclusive, that this is actually going to be negative, implying that between 0 to 1 over e, that's going to be decreasing. And if you plug anything strictly greater than 1 over e, you're actually going to get something positive, so that means that's going to increase. So therefore, with this justification over here, that means this is going to be decreasing, and then for x strictly greater than 1 over e, that means this is going to be increasing. So those are some key things to note before we actually sketch our final product. So let me actually underline this so we actually get an idea. Increasing and increasing. So the last thing to determine is the concavity. I know we get that this is decreasing and increasing, but sometimes you want to determine, like, for all we know, it could be decreasing. There's a point of inflection, still decreasing. So that's where the concavity can lie in between. So that's why taking the second derivative is always a good check to analyze there. Applying the second derivative test. So f double prime of x. So in other words, do the same thing. Just take the derivative of f prime of x, and then same thing again, that you actually use a bunch of product rules and then simplify that out. So we have e to the power x ln of x multiply by ln of x plus 1 and then square, then add this with e to the power x ln of x and then divide by x. Sounds like a lot. So if I plug anything for x, well, strictly greater than 0, if we get something that f double prime of x is positive, that's a concave up. And if it's a negative, that is a concave down. So easily enough that if you actually try a bunch of numbers, you'll see that no matter what you plug in for x strictly greater than 0, this is always going to be positive, and then this is always going to be positive. Always positive, so therefore this implies that for x strictly greater than 0, then that means f double prime is strictly greater than 0, so that means concave up. So I think we have everything that we need. So, and then another thing is that we have x equals 0, so we have 1, so at least that's one point that we can plot. And then another thing, so let me actually sketch out what our graph is. What's nice is that this is strictly positive, so to save this, how to draw the axes, I'm actually just going to draw both the first and the second quadrant. We have at x equals 0, that's going to be 1. So let me just plot that point there. And so we have our critical point at 1 over e. So that's approximately around, like I said, that's approximately 0.367. So if I graph this, so that's 0.6922. Let's see, so that's around here, and then I'd say 0.69 is somewhere around here. So we have that between 0 to 1 over e. This is going to be decreasing, so something like along those lines. So what's nice is that I have an x equals 0 and then that's 1. So that's because that, again, we split this up for a reason. Indeterminate form, and if you were to think about this in terms of a limit and do some differentiation, it's not differentiable over there. So if you know this from both the absolute value cases, that and it's even, that means there actually is cups. So over here, this is indifferentiable. So now if I plug 1 to 1, so that means that's going to be a 1 over here. And then everything greater than 1 over e is going to be increasing. So I'm just going to draw a line like this. And then 2 to the power 2, that's 4. So I'm going to draw that. So I'll plot over here. And then that's also increasing as well. Pardon my sketch. Okay. And then everything onwards above is increasing. Okay. So I just denoted the arrow. And so last thing is that that's one side. This is an even function, so this is actually symmetric over. So if I just do the same thing, so this just flipped over the y-axis here. So here, and then sketch here, then 1. Then that's increasing from here. And then lastly, it's -2 and then +4. So over here, hang on. And then now just connect the dots from all the way over here such that it is mirrored, so like this, and then all the way onwards it's equal. So just like that, that's our final function on what the absolute value of x raised to the power absolute value of x is going to look like over here. And of course, when x is equal to 0, we have 1, just like that, defined point, and then it actually looks like the shape of a W. Oops. And there we have it, a nice W function with a non-differentiable point at 1, the cups, we want to put it that perspective, and there we have it. So yeah, that's pretty cool if you ask me.